Swayam Prabha. Digital India. Educated India.
Hello everyone. So in this class today we are going to talk about the tiering method, essentially the bubble point calculation method, and we'll talk about its algorithm, and in the next class we will solve an example problem. So unless we talk about an example problem, things are not so well understood, right? So here we are going to talk about the bubble point calculations and the process of obtaining or the necessary equation framework, and how you arrive at the tridiagonal matrix formulation in this case is something which I want to highlight. Okay, so before as we start, first let us write down the mesh equations. So I will just quickly try to draw the tray just for the sake of clarity and for the sake of understanding. So let us say this is my jth tray, right? So I have, this is Vj, this is sorry, I should not write like this, I should write like this, Vj plus 1, this is Lj, this is Lj minus 1, you have a side cut, we have defined that as Wj, side cut here is denoted as Uj, the heat component is Q, and there is the inlet feed Fj. We write down the this Yij, this is Yij plus 1, this is Xj, and here we have Xj minus 1, and here we are having Zij. So similarly you have Tj, Pj, and you have Pj plus 1, Tj plus 1, you have liquid and the hyper strings need not to be written down. Here you have Tj minus 1 and you have Pj minus 1, right? These are generally the specifications. Of course, L and the enthalpies are also written down as HVJ and HLJ. I am also writing down the temperature and the pressure of the feed stages, right? So the M equation, the C number of M equation, this is just a recap from the last class. So we'll just go through this quickly. Right, so this is the vapor that is into the system plus liquid that is into the system minus vapor this is vapor leaving the system minus the vapor that is introduced to the system and minus of the liquid that is introduced into the system and minus the feed that is introduced into the system, right, where gamma Vj is the fraction of the side cuts, right. Let this close not to avoid any confusion. So this is the M mesh equations. Then we have the E equation. So Eij is written down as Kij xij minus yij equal to 0. You also have the summation equations, right? Both for the liquid component and for the vapor component. Right. Next we write down the energy equation also. So this is the energy that is going out, or the enthalpy leaving the system. In the form of vapor and in the form of liquid. Right. This is the vapor entering the system, and an enthalpy to the vapor entering the system, and this is the enthalpy of the liquid entering the system, and this is the enthalpy of the feed stream, and here is the external heat. Right. Now let us see that if n number of stages, n number of trays are specified, right, are specified. Let us say you have the tray nomenclature as like this. Right. So I mark this one as the total, the top one as total condenser, and the bottom one as reboiler. Right. So let us draw the streamlines here. Stream connections like that here. So this one is V2, right? This one is L1. Please note the subscript. This is a side cut D. This is a feed tray, right? So there will be some some intermediate stages, like till from 2. It is not like 1, 2 and then NF. Similarly here also there are some intermediate stages which is not shown here. So the feed to the feed tray is F, right? FNF you can also write, something like this, and the reboiler is B. I mean the B is the side cut or the flow rate from the reboiler, right? So from here the specified variables for this case are of course the number of stages that is known. Then you have Fj, of course number of stages doesn't come in the part. Fj, then we have Zij, Tfj, then you have Pfj, right? Then you have D in the problem, then B is also specified, right? Or B is something that you can also calculate out from the overall mass balance. And let us say the pressure in the system is specified for Pj for all the stage, either pressure or temperature, whatever one of them, either pressure or temperature is specified for all the stages. Okay, so now from the let us work out the equations, and if you try to form the generalized equation, you can relate each of these coefficients in the material balance, the heat equations together, right? So what we are going to do, I am going to write down the material balance and the, maybe I can write it down here, the equation together, right? ME equation together. So what I get, I want to remove all the xij's, all the yij's into xj's. So this is Vj, then I have from the equilibrium relation as Kij, Xij. So this part is nothing but your Yij before, and plus you have 1 plus gamma Lj, Lj Xij, then we have minus of Vj plus 1, Kij plus 1, Xij plus 1, minus L j minus 1, Xij minus 1, minus Fj Zij is equal to 0, right? This is the Mej equation. I can write it down. Now let us look into how does it turn out for the first stage. So Me I comma 1 will be L1 plus D, isn't it, as Xi1 minus V2 Ki2 Xy2, and rest are 0 because gamma Vj is equal to 0, Vij for stage 1 is equal to 0, Fj is equal to 0, isn't it? Similarly, Me I comma 2 can be written down as V2 Ki2 Xi2, right, plus L 2 Xi comma 2 minus V3 Ki3 comma Xi3, right, minus Li Xi my I comma 1 is equal to 0. So all the vapor and the liquid flow rates are there. There is no side cut, and of course there is no feed tray. Similarly, for the, I am only writing some of the important ones, and the rest would be all similar. M2 would be similar to M3 and M4, etc., except for the feed stage, right? So VNF, right, KINF, then you have XINF plus, so all this would be same, LNF, XINF minus VNF plus 1, KINF plus 1, XINF plus 1 minus LNF minus 1, XI comma NF minus 1, isn't it? And then we have the feed, that is FNF, which is nothing but the feed, ZI comma NF. This would be equal to 0. So from 2, so ideally what we get for 2 to NF minus 1, we have, so from 2 to NF minus 1 and NF plus 1 to almost the stage before the reboiler. For all these parts, you have gamma Vj, gamma Lj, and Fj all are 0. These parts doesn't come in the picture generally, unless you have some specific multiple feeds and all, or different side cuts and all. Generally this does not exist, right? So for the reboiler, let us also write down for the case of the reboiler, which is the nth stage. So please note the total condenser and the reboiler are part of the stage numbering, right? This is the reboiler. So for the reboiler we have, I hope now this is clear to everyone. For the reboiler, right, and you have only the liquid part, Ln minus 1 Xin minus 1 equal to 0, isn't it? So now in all the equations, if you look carefully, particularly the ME equation, if you look carefully the ME equation, you will see that you are having, so here you are having terms of Xij, right? You are having terms of Xij plus 1 and Xij minus 1, isn't it? And of course Zij, so Xij is the unknown quantity, right? So you are having here Xij plus 1 and Xij minus 1, right? So this ME equation, right, so this ME equation that we have written down, right, can be generalized in this form, sorry, generalizing the ME equation as let us say Aj Xij minus 1. So the coefficient for the j minus 1 component, j minus 1 term is Aj. Then let us say B, sorry, also want to write as Aij and Bij, sorry, Xij plus Cij is the coefficient of the j plus 1 term, and I can write this as Dij. So if I compare the coefficient, and this, I mean, I can write Aij as Alj minus 1, isn't it? Then Bij, the coefficient of the term including Xij, is minus of you have 1 plus gamma gamma Lj Kij, then you have Vj plus Lj, so this is not gamma Lj, gamma Vj, Lj plus Uj, right? So if I go back, so this is the term, so you are having for 1 plus gamma Vj Kij, that is 1, and then again you are having 1 plus gamma Lj, this is the coefficient of Xij parameter. So this part I can also write down as 1 plus gamma Lj, isn't it? This I can write down, and minus is given in front of this equation because we are trying to write down both in the other way around. So that's why I have given this as a minus. If you have noted down, the j minus 1 term is written down as plus Lj minus 1, right? That's why the B component is minus, and Cij is equal to Kij plus 1 into Vj plus 1, and dij is equal to minus zij fj. So this is how I can form the a, b and the c coefficients for this mij equation. So if I am going to write down the ME equation for all the individual trays or for all the individual stages, what do I get? I get a matrix formulation. Please note that I will be getting a tridiagonal matrix, isn't it? Where the tridiagonal matrix, I have the first term as bi1 ci1. This will go on. Then I am having ai2 bi2 ci2, and then you have zeros. Right. So this will continue, and let us write down the n minus 1 stage. So I will be having something like iy n minus 1, bi n minus 1, and ci n minus 1, and the last stage would be ain and bin. Right. So this is the tridiagonal matrix that we are getting here, and of course each of these rows would be multiplied with xi comma 1, xi comma 2, then xi comma n minus 1, and xi comma 1. So such tridiagonal matrix forms needs to be prepared for all the individual components. This is for one component. Similarly, we will have for other components, right? And if you recall from the previous case for I, so this is n cross n matrix, right? So if you recall here, for the stage, for the tray 1, you will find that there are no x0 components, right? So from here I can write down, if I try to write down the individual coefficients, I will see that my b1 is equal to L1 plus D, isn't it? And C1 is equal to, so this is minus of this, and C1 is equal to V2 into KI2, but A1 is equal to 0. A1 doesn't exist, right? And similarly for the last tray, for the reboiler tray, you will see that there is no term, related to xn plus 1, in plus 1. So it means Cn in this case is also 0, right? It doesn't exist. Cn doesn't even exist. It's not that it is 0, but it doesn't exist. Here also A1 doesn't exist. So this satisfies the structure of the AIN and this tridiagonal matrix, where for the first row you don't have A1. Similarly for the last row you don't have your Cn, right? So in short, this can be, so this matrix I can call that as alpha, and this is the X matrix, and that is the, whatever beta or D matrix. So I can write alpha X is equal to some beta matrix. This is vector, X is a vector, and this last column which we have is a vector. So X is a vector and B is a vector. So something like this can be written down, and I can, from here I can find out my X is equal to inverse of this matrix into B. So this is the classical way, but here this is a tridiagonal matrix system, so the best way is to use the Thomas algorithm, right? So now let us talk about the solution strategy. What is the solution algorithm here? Algorithm for this bubble point calculation. So first you assume the tier variables. So Vj and Tj are the tier variables for this problem, right? So of course you need not to assume both of them, but it is often useful or it is often helpful if you assume both of them, but at least one of them needs to be assumed, because you know that out of this Vj, Lj, Tj and Pj you have to guess one of these values. So we are considering that apart from one of these values, you guess for two values to begin with. Next step is calculate Lj from material balance. You can easily calculate that for each stage from the material balance. Then calculate Kij from vapor liquid equilibrium. The next fourth step is for each component construct this tridiagonal matrix and solve for the tray composition. See, once you know your Lj, Vj, Pj or something, these quantities, I mean pressure etc. Pressure is generally also specified. Pj is known, then you can calculate out your Kij, right? And then for in the say expression, once you know your Kij, and then Vj and Tj are already guessed parameters or assumed parameters, you calculate your Lj. So all the coefficients of the TDM will be known. So for each component, if there are like let's say 10 components, for each case you have to construct a TDM and solve for the individual components in the trays. So all the component composition in each of the trays will be known by solving this. Of course, how will you going to solve? Using Thomas algorithm. Otherwise the calculation would be extremely inefficient or slow. Next is that this is a very important stage. Normalize tray composition. Please note that whatever the tray compositions that you have got for each of the individual trays, the summation of all the components I mean by mass balance has to be equal to 1, but since you have already assumed your Vj and Tj which are not the actual solution, it is not sure that the summation, I mean you cannot ensure that the summation of Xij of over I, right, not over j, for all the components in each tray, these may or may not be equal to 1. So better is to normalize them, that is the technique. So what is the normalization you do? That Xi bar is equal to Xi divided by Xi, right, summation over all the components. So if you do, then it ensures that the summation of this normalized tray composition will be equal to 1, right. This is kind of normalization. Next is to calculate the bubble point. Calculate the bubble point temperature for each tray, right. And how do you do it? You use the other summation equation, Kij, and to get this you use the normalized tray composition. This is nothing but summation of Yij, but calculation of the Y is you relate it as with the normalized composition. This is equal to 1, right. So from here you already know the this Xi, this normalized tray composition. So Kij is a function of temperature, right. So this is a function of T bubble point temperature, right. So from there you can work out what is your bubble point temperature, right. So now since since this Tj and Xij, this whatever are known, the tray composition and the tray temperature are known, calculate Vj, the vapor flow rate in each of the trays, vapor flow rate, vapor flow in each tray from the H equation, enthalpy equation, because in the enthalpy equation the equilibrium constant is already known. From the step 6 you have already calculated out the equilibrium relation, provided temperature is known, equilibrium constants are known. Then your Vj, your Vj is the only unknown in that equation, right? And finally what you need to do, you need to check that this whatever you have assumed, right, whatever you have assumed and whatever you are getting from step 7 are same or different, relatively speaking, and this difference or whatever this relative error we call has to be done over all the stage, summed over all trays. So this has to be less than a tolerance. Similarly, the Vj values in this case and whatever you have assumed are relatively they are close or not, that is something has to be checked, again summed over all trays, right. So over all trays, this, if you check this relative error as the difference of the temperature and the difference of the vapor flow rate across all the trays, they has to be less than the specified tolerance, right. So this is a check. If not, then this new values of your Tj and Vj whatever you got from step number 7 has to be used in the first stage as your initial guess, and then you redo this calculation and continue this checking. So please note that in each of these step iterations you have to set up or you have to solve the tridiagonal matrix and get the individual tray composition and then check for these two criteria, right. Check for the temperature as well as for the vapor flow rate. These two criteria needs to be checked for convergence, and each of them have to be satisfied individually, right. So this is a summation you need to do over all the trays, because all the tray compositions or all the tray values may not come same. So you have to do the summation. So the relative error has to be summed up, and then only it should be below a certain tolerance value. So typically this epsilon is generally, at least it should be less than 10 to the power minus 2, at least 10 to the power minus 2 or 10 to the power minus 3 for convergence. Okay, so I hope all of you had a proper understanding of the solution algorithm of the bubble point method or the bubble point calculations using the rigorous method of the tier variables, and this will of course, as you understand, will give you the understanding or the calculation of the tier variables and the individual tray temperatures, their compositions, right. So in the next class we are going to work a small example problem, so that it will be more clear on how to put the numbers and how to do the calculations. I hope all of you found this quite useful. Thank you.